Okay, ladies and gentlemen, today we're going to talk about solving a system of linear inequalities. Everything we've looked at so far has been equations. Now we're going to look at inequalities. So do you remember what an inequality is? Okay, so we've got, for example, y is greater than or equal to 2x minus 3. That's a linear inequality. So how is graphing an inequality different from graphing an equation? Keep in mind things like dotted lines and shading. So let's take a look at an example and see if we can remember exactly how to shade and whether we need to do a dotted line or a solid line. So this first one here, we've got y is less than 2x plus 2, and we've got y is greater than or equal to negative x minus 3. So remember, we are always going to start with the y-intercept, so I'm going to put my first dot at 2. And then I need to do my slope, which is rise 2, run 1. So rise 2, run 1. And is this going to be a dotted line or a solid line? Well, it says less than, it does not say equal to, so it needs to be a dotted line. And it says less than, so that means I'm going to shade less than the intercept. Alright, and the second equation then, I'm going to change colors here real quick. We've got y is greater than or equal to negative x minus 3, so I'm going to start at negative 3. And I've got a negative slope, we're going down 1, right 1. And this is going to be shaded greater than or equal to. So this is going to be a solid line, and we're going to shade where it's greater than. So now what do you notice here? Remember, we're solving a system of equations, and a system of equations has to do with where they intersect. So what is my final solution in this circumstance? Well, I'm going to shade it in with yellow here. It's everywhere where those two shaded regions overlap. So my final solution is where they are overlapping. Okay, so you want to make sure you shade that in extra dark so we can tell where your final solution is. Alright, let's try one more. We've got 2x plus y is greater than or equal to 4, and x plus 2y is greater than negative 4. Notice these are in standard form, so we need to put them into y equals mx plus b first. And I'm going to do this other one while I'm at it. Divide both sides by 2. So y is greater than negative 2. Remember, that's got an invisible 1 there, so that's negative 1/2 x. Alright, so let's go ahead and graph the first one then. We're starting at our y-intercept of 4, and we're going down 2 over 1. And is that a dotted line or a solid line? It's going to be a solid line because we have the equal to sign. And we're shading where y is greater, so that's above. Y is greater. And the second line, I'm going to change colors again. Having two colors when you're graphing these inequalities really makes things a lot simpler to be able to see where they're overlapping. Alright, so we're starting at the y-intercept of negative 2, and we're doing a negative slope, down 1 over 2. And notice this one does not have an equal sign, so this is going to be a dotted line. And we are shading where y is greater than, so that's all of this area. So where is our overlapping happening? In this area here. So that's where my final answer is going to be, where the two shaded regions intersect. Alright, so let's look at a couple word problems here. Before the word problems, special solutions. Because remember, you've got those two options, no solution and infinite solutions. So let's see what that means when we're dealing with inequalities. So notice here we have the same slope. That means that the lines are parallel, right? And we have shaded where it's greater than, and we have shaded where it's less than. Do those areas overlap? No, they do not. So that means that there is no possible solution. All right, so I want you to think about what infinite solutions would look like. Is that possible? So if you think about when we graph something and we're looking for the intersection of where those areas are overlapping, technically we are talking about infinite because this goes on and on forever and ever and ever, right? But it doesn't include all areas. And here they don't overlap at all. So is infinite solutions truly possible? Could every single area be overlapped? The answer is no, it can't. All right, so now let's look at a word problem. The senior class is sponsoring a blood drive. Anyone who wishes to give blood must be 17 years old and weigh at least 110 pounds. Graph these requirements. So our two variables here, we're going to let x equal their age, and we're going to let y equal their weight. And I know the answers are already here, but it's more important how we get to that answer, okay? So if we got x is the age and y is the weight, we know that they must be at least 17 years old. So that means they have to be greater than or equal to 17. And they have to weigh at least 110 pounds. Same thing, greater than or equal to 110 pounds. So these equations are going to be horizontal or vertical lines, oivooks. So you notice x is greater than or equal to 17. That's a vertical line at 17. And it says greater than, so where is it greater? And we got y is greater than or equal to 10, so it's a horizontal line, and where everything is greater. So the area where those two things are overlapping, those are the people that can donate blood. If you're 15 years old and you weigh more than 110 pounds, you can't actually donate blood. If you're older than 17 and you weigh less than 110 pounds, you can't donate blood. And that's to be safe and make sure that there are no other complications. All right, so what I'd like you to do is to practice these skills. You've got only the evens and a word problem. I know you're going to think the word problem's too hard, but just try it. I know you can try it.